My name's Terry Little. I'm Development Engineering Manager at FIT and located in Irvine, California. I've been in connector and tooling design for a long time. I guess we won't reveal any age, but just joking. But prior to coming to Foxconn FIT, I had 20 years as a mechanical engineer in tooling, um, uh, fixture design, tooling, etc. at FCI, which prior to that was DuPont Berg Electronics, but now it's FCI's still is part of Amphenol. But prior to that, I had a strong experience in stamping dies, went through a 10,000 hour, 5-year tool and die apprenticeship program, became heavily involved in stamping dies, tooling, as well as machine build. So connector design has always been in my realm for a long time. When I came to Foxconn, it was prior to FIT, back in 2003, I started developing board-to-board connectors, Cat5e, PoE+, FPC connectors. And then once we started getting into more of the high-end consumer stuff, which was obviously USB Type-C, I was one of the main contributors to that. And more recently, QSFP double density, SFP, OSFP, and now we're getting into QDD 1600, OSFP, XD, etc. So heavily involved in high-speed cable and connector design and also thermal development. I also represent FIT for the IEEE 802.3 standards, QSFP DDMSA and OSFP MSAs, as well as Open Compute Project for immersion cooling environments for signal integrity. So we're going to talk about the path forward to 224 gig and where we are and what we need to do to get there. AI is driving a lot of this, and the more advanced demands for complex computing power and large storage capacity, the higher speed interconnects are definitely a key feature and attribute of this for these increasing data rates. So in order to get out to and achieve these data transmission rates up to 224 gig per second, we have to develop connectors and cables that have stringent, tolerancing, et cetera, and to maintain the best performance. We've worked on and well within our HSIO portfolio, our OSFP 1600, QSFP DD 1600s, including SMT connectors and cages. And we also have to develop the thermal attributes for these riding heat sinks that go along with it. And ultimately, at 224 gig, if we have 8 lanes, we would be pushing 1.6 terabit per connector. That's the baseline that we're working towards. Okay. So if we go on, as we talk about this path forward, you can see in the lower left how the Ethernet speeds have gradually increased for a while, from like the 80s to the 90s, 2000, 2010, and we started getting into 2016. We were looking at QSFP DD 56 gig. Then it started to take a sharp incline straight upward to 112 gig per lane. And now we're even looking towards more like vertical towards 224 gig, right? So these demands placed on these data centers are constantly rising. So for all these components to perform at their full potential, like I said, the cables and connectors require improved designs and development more towards more stringent manufacturing tolerances. For example, the stamping lead frames in these connectors, when we would see things at, say, 25 gigabit per second, 50 gigabit per second, as we started to progress into 112 gig and beyond, we start to see, wow, we really need to tighten up all the mechanical tolerances, the lead frame stamping gaps. Everything is critical now. Okay, so that's what we want to make sure we convey that message. This is our networking I/O roadmap, in some of the SFP series as we progressed over the years. It's items and that are readily available: SFP, SFP Plus, SFP 28, SFP 56, QSFP 56, etc. Now, like I said, when we started to get into QDD, for example, 800 came along sometime around 2022, a little bit before. Then we started to realize, well, the industry's changing, right? Even the system boards that some of these connectors sit on, there may be too much loss in the system board. So now we looked at the cabled IOs, the cable type connectors, where we kind of attach the raw cable directly to the contacts of the connector and like fly over to the ASIC. And so that's important to understand. That's part of the development aspect. QSFP-DD, has moved up now to 224 gig. And as we're looking at the recent release of the spec, we're at, for example, QSFP DD, we're at Rev 7.1. So it's really increased a lot over the years. And likewise, OSFP is approaching 224 gig. And as we look out beyond 2025, we see OSFP XD as going to be one of the main players, possibly even being used for PCIe 7. So XD could have, dual roles as far as Ethernet and also for PCIe 7. If we were to achieve 224 gig, which is our target for the connector design, OSFP XD with 16TX, 16RX could ultimately be 3.2 terabit per second per port. So there's a lot of things that are in the development pipeline. And now if we look at the connectors themselves, these lead frames, as I mentioned, stamping is critical to this, to make these connectors work. And if you look at, for example, from QDD 800, 1600, OSFP 112, but if we look at number 4, OSFP 112 2x1, if we go to the upper port, I put a red box around, we call rows C and D, which are the longest lead frames. That's going from the SMT tail at the bottom from the system board up to the IO side where the contact bellow is. If you actually look at the longest lead frame and you unfold it, you lay it out in its flat state, it's about 36 millimeters long. That's longer than an inch. So you got to be able to design your connector to accommodate the new standard for IEEE, which is going to say, well, the fundamental frequency or the Nyquist is going to be 53.125 gigahertz. And even if we look at beyond for 56 gigahertz, that's more in our design target. And then if we look below at OSFP XD, even the longest row is a little bit shorter than the longest row of the 2x1. It's about 29.5 millimeters. So we chose the 2x1 as our target for our stamping development, because that's going to be the biggest challenge. How do we get across that long signal path down to the board, right? With that being said, we actually tooled some connectors back before DesignCon, which probably towards the end of 2023, December, and then had them ready to demo during DesignCon of this year. And you can see the OSFP 2x1 SMT connector that's shown in the picture. I highlighted the upper port in a red box for that reason. We tested the port. This is not simulation, but actual test data. Now, I want to point out that the MCB, or Module Compliance Board, and the HCB, or Host Compliance Board, were our original connector MCB and also HCB designed for 800 gig. So we didn't have 224 gig per lane HCB and MCB at that time, okay? So we had to use initially the first pass to test the connectors with our 112 gig per lane HCB and MCB. And then as we gradually increased the development, we obtained the Wilder 224 gig HCB on the right. You can see the picture. where that does improve the insertion loss and shows, obviously, because it's not the host board, very long traces, it will gain about 5 dB of loss. But we still have our our MCB, our module compliance board, with the 3-inch Huber-Schumer cables coming out the back. But if you look at the actual test data that I'm showing, and again, the boards that were used are under next generation development, so they're going to improve in the next phase. So this insertion loss will even get better. But this is mated test fixture, and out to 53 gigahertz, which was Nyquist, we still have pretty linear behavior. We're going to improve this because this includes the test fixtures. So the next set of test fixtures will gain a little more in the insertion loss design. Return loss is well behaved out to 53 gigahertz, under minus 10 dB. But then if we look at the near end crosstalk, for instance, using the HCB MCB that's shown in the upper left picture, we're still about minus 50 dB of near end crosstalk with maybe a few variant pairs, one pair, maybe a little bit above, but we'll improve that as we go. But this is actually tested, out to, we actually tested these to 67 gigahertz. So I can go back one slide and say, well, this Keysight PNA we have is capable to test out to 67 gigahertz. So that's typically our capability across our test data, okay? And if we look a little farther into, okay, how do we correlate from simulation to actual measurement? Well, here on the bottom screen is still the same image of actual measurement of the connector. And if we go to the upper screen, this is simulation of rows C and D. Remember those long lead frames that were inside the red box? We pretty much match up within a dB or two of each other from simulation to measurement. So the correlation is very good. Now, I do want to point out the limit lines you see are still from the IEEE 802.3 CK spec. DJ is still not finalized yet, so we anticipate that these limit lines will change. And once the IEEE 802.3 DJ spec is finalized and ratified, then we will obviously retest to the new spec limits. But this is just a reference. I just wanted to share with you that the correlation from measurement to simulation is very good. Okay. And then heading towards DesignCon of this year, we wanted to see how far we could push this upper port. And we did use two boards, one left, one right, same upper port, same connector. And again, I want to point out this is a 2x1 OSFP SMT connector mounted to the boards. Okay. And we connected a 1 meter passive 26 gauge passive DAC between the two. And using our MCBs with our passive DAC, we did do some early measurement. And again, these are earlier test fixtures. So these test fixtures will improve. The connector and cable obviously will improve. But overall, the performance is relatively behaved. Some ports, we did see some pairs are a little bit above 30. I know probably we're going to be targeting maybe 29.4 dB, but this will be remeasured later. This was the initial sample that we did for DesignCon. And actually, one pair, for example, TX7 came in about 26.7 dB. So that's actually a pretty good performance. So there's a little bit of work that will be done in the fixtures, but this includes all the test fixtures, the 1 meter passive DAC, and the 2x1 upper port measurement. So when we went on to DesignCon, we were actually the only company on the floor to demo 224 gig interop with Synopsys and actually in an SMT connector in the upper port. And Synopsys 224 gig, we successfully linked up to their 224 gig SerDes at DesignCon, and we're able to run, the whole length of the show for a few days, about e⁻⁶ bit error rate. So that was a monumental achievement. Again, focusing on the upper port of the 2x1 SMT. Okay. And actually, for DesignCon, we did plan to show two different connectors. One was our 112 gig connector, which is another demo, which I'm not showing on this page. But we did focus on the 2x1 upper port for 224 gig because of the development of that long lead frame. And we were successful with it. Now, heading into the 224 gig 1x1 SMT, the SMT connector module that we have inside the housing is designed the same, so it can plug into both the lower port of the 2x1 housing or the 1x1 housing. And this one is being redesigned for 224 gig now, using the same contact recipe that we did for the 2x1 upper. And given the anticipated spec for IEEE 802.3DJ, which again isn't finalized, but we anticipate that these are going to be the numbers for mated connector, is about 2.9 dB is what we anticipate will be the requirement. For device under test only, using the connector, including some PCB trace, some Goldfinger, also some MCB via, a little bit of that included. This would be differential insertion loss. So we're well within the 2.9 dB. You can see out at Nyquist, we're probably, even at worst case, say 50 gigahertz, we're about 1.8 dB of loss. So we've got a lot of margin. And the same goes if we look at differential return loss, even out to Nyquist, we're still about minus 11 dB at the worst case. So this is going to be the 1x1 224 gig SMT connector. And again, looking at mated test fixture now, again, we don't have spec limit lines for the DJ, because this is based on CK, but we kind of just showed, okay, in the upper limit, we were still very linear at mated test fixture for both insertion loss and return loss. Obviously, mated test fixture is going to bring us in around minus 20 dB, you can see here. But again, once the IEEE 802.3 DG spec is finished, we will test to accordingly. Again, based on the CK spec, which is out there, we know, for example, integrated crosstalk noise calls out a variable of 1.5 millivolts. And for far end crosstalk, it's 4.2 millivolts. So we looked at the integrated crosstalk noise, or ICN, as we call it, based on Next and Fext, and we're well within the limit lines on this connector design. So that's where we are on the 1x1. For OSFP XD, originally, we're starting out at 112 gig to develop the SMT connector. It's 4 rows. And even at 4 rows, at 16TX, 16RX now, at 4 rows of that, at the 16 lanes would still give us a 1.6 terabit across the module, right? So this is in development. We're focusing on bringing up XD in Q3. And we're just showing the 3D model with the Type 2 module, and also the writing heatsink here. And then this is just the side view of the connector. Ultimately, we would like to establish 224 gig, and that's our goal. So that would give us, if we can approximate, 3.2 terabit per port. But we are in the process of doing the first design aspect of it. The footprint is a JL footprint on the front and an LL on the back, just like the the MSA spec calls out. And the pin assignment, at least for when we do our boards, our HCB, MCB, or our MCBs, the beauty of it is we can still use the same MCB for both 2x1 as well as the OSFP XD. You know, OSFP provides 32 contacts for 16 diff pairs for high-speed transmit. So if we're able to achieve, you know, this pin assignment and this development for 4 rows, 16 TX, 16 RX, again at 224 gig ultimately, that would be a plus. And again, the footprint of the 2x1 shown can also accommodate the OSFP XD connector. Okay. We are still in development of this, so I'm just showing some simulation. We still need to be have a little more cleanup out towards a higher frequency, which is under development now, but we feel we can easily achieve it as we progress towards the next development stage. So our anticipated development timeline for XD, like I said, is Q3. And that's our target. Now, probably what we'll end up doing is designing the connector for 92 ohms impedance. We know OSFP XD has, like I said, a mainstay for Ethernet, but also a candidate for PCIe 7 for external cable. And then on our roadmap as well, we don't have any data to show on this, but this is what we call our FPIO cable type. I know I mentioned when I looked at our roadmap and showed you our roadmap, as we progress to these higher data rates, we look at actually, you know, a cable type connector instead of an SMT coming down to the board. So this is one that's in process. FPIO is our trademark for FastPass IO. And this is future development. And we want to focus on 224 gig per lane. Okay. So that takes care of signal integrity stuff. Now, when we get into these high speeds, along with that, as we know, there's going to be more and more of an increasing thermal demand, right? So as the data rate of these connectors double, and we go from generation to generation, we went from 50 gig to 100 gig, and then that gave us the 800 gigabit per second, right? 112 gig per lane. And now if we look at 224 gig, we could be looking at 1.6 terabit per second per lane, which we are focusing on, both OSFP and QSFP-DD. And if we look at XD, if we chain that same 224 gig per lane, XD could accommodate 3.2 terabits per second. So the heat dissipation per module is going to reach above 30 watts. And we've already, you know, tested and simulated to that already. And just thinking a few years ago when we were looking at QSFP, we were down around 3.5 watts. So things are going vertical. And along with the signal integrity and the demand for the signaling rate, the thermal is climbing. So with that being said, the thermal load in the module could be on par with modern logic processors. So the next generation modules need to be improved to manage this increased heat dissipation. So we have an increasing consideration and ongoing project for thermal development for 224 gig. And it focuses on 3 key items. One, we need to understand the limits of the heat sink performance under compliance constraints, and also considering different changes in geometries, materials, airflow rates. You know, the system guys that we get involved with, you talk to, you know, what is our airflow rate? What kind of materials, what kind of coating can we put under the heat sink to improve? And that sort of thing. And then R&D for new heat sink type designs and new thermal interface materials, or TIMs, that can withstand repeated shear loading because the cables have to plug in and out several times or a few hundred times. So we can't have a TIM peel off or flake away when the module's mated and unmated. And so ultimately we would simulate first, based on that, we would prototype and test the different heat sink samples. So we use what's called ANSYS IcePack to simulate the results, and then we verify in a wind tunnel that's in our lab for correlation. Okay, so I'll talk a little bit about that. Using ANSYS IcePack, we looked at, in this case, remember we looked at the 2x1 upper port for simulation, okay? That was because of the long lead frame. But for OSFP thermal, we looked at the lower port, okay? Because we know in our past experience of a 2x1 connector and cage, the lower port always runs hotter. Now, in the case of QSF-PDD, we recently, and I'll talk about that later, we recently increased the height of the upper port by 1.87 millimeters. That's to give a little bit more space in the bottom port for the riding heat sink. And that gains us a few degrees of thermal performance, which is very critical. And if you look at, we were focusing on 32 watts. Now, again, I was saying that we're looking above 30 watts. We put our efforts on 32 watts, but the ambient is not room temperature. The ambient is 45 degrees C. And a lot of our customers are talking, you know, this is our operating temperature. So this would be something we have to consider immediately. So when we did the simulation, we have 3D models and we work with Multilane. These are the thermal models they provided us. But if you look closely, there's a lot of different areas. For example, TS3, TS2, TS1, shell, TS1, et cetera, et cetera. There are little, what we call resistors that we can turn on and off. And obviously in simulation, we just assign a value. But the hot spots are closer to the middle where the bright red boxes are. That's more of the DSP area. And I put a few arrows around what we simulated using, I think it was 11.4 CFM was our fan flow and 3 inches of water. So when we measured or simulated, you could see our temperature ranges of those two hotspots around 71 to 73 degrees C. That's in simulation, okay? So after we got an establishment at 32 watts for 45 degrees C ambient, we actually went and built some heat sinks with our cages. And this is our actual test vehicle. This is a very large wind tunnel, has the capability to measure with air speeds ranging from as low as 5 cubic feet per minute up to 500 cubic feet per minute, okay? So we can accurately monitor the airflow and pressure drop in the chambers through here. Now, if you look at the front, we have kind of an outrigger box here that we built. That's like a chamber that would mimic areas of the 2RU or the 1RU. And you can see here's the 2x1 OSFP cage that's attached inside with the board inside. And so these modules we purchased from Multilane, and again, this is exactly the same type of module that is based on the 3D model that we simulated with. So everything's identical. And out of the back of the module, there's usually a connector and cable that will come across and will go to a controller card here. You can see it. And then from there, that controller card has a USB cable that goes to the laptop that runs a GUI, and that we can turn on and off and assign different values to different areas of the module. So we know exactly what we're monitoring, where we're monitoring, okay? Now, if you remember those two areas I pointed out, one TS2, TS3 was 71 and 73 degrees C. That's simulation, okay? When we actually tested it in the wind tunnel, we looked at the same TS2 and TS3, and at 3 inches of water, and it actually was around 12.5 CFM. And again, this is with 32 watts. 32 watts with 45 degrees C ambient. And we actually measured the same performance of actually 71 degrees Celsius, and came across both relatively close to our simulation. So the correlation test said, well, it's relatively close. And we noticed that this would be our direct correlation test vehicle that we use for our thermal testing. Okay. And then finally, as I get to the end of the presentation, we participated in QSFP-DD thermal white paper. And the one on the left, these are some of the contributions we made. The one on the left, there is actually a project also ongoing with the university that we're developing a TIM, or a thermal interface material coating for the underside of the heatsink, something that must be durable and also can improve the thermal attributes of these. This is showing the riding heatsink flipped upside down. So this is where we would apply the TIM. So that's a project ongoing with the university now, and it's in process. And then one of the other ones that I talked about that's in the published white paper, and I think this white paper is actually available on the QSFP-DD MSA website. This is what I was saying. We increased the upper port by 1.87 millimeters. And that allows, you can see between the upper and lower port, a larger heat sink to improve. It can improve the airflow because your opening for your grid is getting bigger, but also it's going to improve the thermal performance of the bottom port because the heat sink is now going to grow. And so this actually concludes my presentation and where